All right, here we are, the last one. So his name is Jeff Dillon, and he's going to speak on lunar rail gun and Mars atmosphere laser. So let's give him a big hand. Wake everybody up. Okay, thank you.
All right. Hi, everybody. Welcome. It's the last session of the day, so I won't try to keep you too long, keep you between now and here in the banquet. So let's see what we can do here. So my name's Jeff Dillon. I was on the Mars VR panel earlier today. In addition to working at Unity Technologies, I also have my own aerospace research and development company, Pure Rockets. It's located in Hayward, California, not too far from here. And it's been a big passion of mine over the last 4 or 5 years. So what you're going to hear tonight is the first time I presented any of this information, so we'll see how it goes. I'll welcome your feedback and your comments. It's also my first Mars Society conference, so it's especially exciting for me, so I'm really glad to be here. Thank you. So what I'm going to talk tonight, I basically have 2 talks. The first one is going to be on, originally it was called a railgun launcher, but it's been expanded a little bit more since then. And so I'll be talking about that. And then secondly, I'll be talking about my Mars atmosphere laser, and I'll be discussing what that is once we get there. So discussing Mars transfer. So what I'm proposing is a lunar-based launch system. This is something I've been working on for about 4 or 5 years now. I'm actually working on a propulsion system currently. As I said, I work full-time at Unity during the day, and basically all that income goes to fund a very expensive rocket hobby, as some of you might be familiar with. So, you know, I am incorporated, but, but anyway. I basically have dumped all my retirement into this too. I have a very understanding fiance that I love very much. Not for just that reason, there's many reasons, but bless her heart. So what I'm proposing is a lunar-based launch system, and I'll be going through the astrodynamics of that and how that all works. The advantages would be you could frequently launch small payloads. So what I'm suggesting is smaller payloads, 2 kilograms or less, launch from the lunar surface to Mars. And the proposal here, I mean, theoretically, you could launch once an hour, for example. One of the biggest advantages of doing a moon launch is, and I'm going to be describing the astrodynamics around this, is you could launch anytime. It can take a little bit longer than a Hohmann transfer, but in many cases, more than half the cases, what I'm going to be discussing is more energy efficient than a Hohmann transfer. So I'm considering 3 launch systems. Originally, I was looking at a magnetic railgun. We've been doing some work on that, and those things are monsters, to be honest. The Navy's developed one that launches a projectile at about 7 kilometers per second. It's going to be mounted on a destroyer. It's a weapon, of course. So what I'm proposing is, similar to that capabilities. I only need about 3 kilometers per second, so about half the size of the Navy rail launch. So it's within today's technology. Another possibility is a light gas gun. Using hydrogen or helium is in a light gas gun. I won't go too much into that. And then lastly, kind of what I'm leaning towards now is just traditional chemical propulsion. So when you launch from Mars, of course, when you launch from the moon, of course you need to get the infrastructure to the moon first. I'm not naive enough to think that that's not going to be, an issue, but it's not that difficult. We've been to the moon, we can make it back. So what I'm proposing is your typical scenario. Let's say you have some settlers on Mars, they've been there for a short time, and there's a medical emergency, and you need to get some medicine to them. So you need to get it there as quickly as possible. So you have several options. You could wait for the next scheduled mission. As you know that the interval between 2 flight opportunities from the Earth is every 26 months. And then you do a Hohmann transfer and you go directly to Mars. So you could wait for the next scheduled one if there's one coming up. You could develop a new mission, very expensive, especially if you're going from the Earth to Mars. I mean, we're talking $1 billion just for, or more, for a rescue mission. Or you could do a lunar launch. And once you have the infrastructure there, I suspect you'll be able to get a spacecraft from the moon to Mars for tens of millions of dollars, if not less. So what I'm going to talk about next is ballistic capture versus the Hohmann transfer. So you're probably familiar with the Hohmann transfer. It's well known. And basically, for those of you not familiar with it, it's where you just hit the gas and go straight there, turn around, hit the gas and slow down and land. That's briefly put. There are some other nuances to it, but the disadvantage is that just the way that the planets line up, Mars and Earth have to be in correct orbit around the sun, and that opens up the Hohmann transfer window, and that only happens about once every 2 years. It's really the only way to get humans to Mars, though. What I'm proposing here is definitely not for any organic material. This is just for supplies. But to get people to Mars, we're definitely going to want to use the Hohmann transfer and wait for that 2-year window. Another disadvantage is the delta V can be very time critical. So when you're approaching Mars, you need to slow down or speed up depending on your trajectory. But you have seconds to be able to time that just right. And you have to burn off sometimes 3 kilometers per second in about 15 seconds. It's very time critical. So you're hitting the brakes hard. And if you miss that window, you miss Mars. So that's not good. So it's very time critical. Ballistic capture, on the other hand, and this is what I'm proposing, it was actually, the next slide talks about it. It was popularized by a professor at Princeton, Dr. Edward Bell Bruno, and we've talking about that a little bit. But what it does, what you see here, I'm launching from the moon. You reach about just moon escape velocity. That's all you need, about 3 kilometers per second, and you're on your way to Mars. And so you swing around the Earth to get a little push there. And then instead of heading directly to Mars, you simply head to any location in Mars orbit and you park it there. A few adjustments are needed, but basically the premise here is you're traveling either a little bit faster or a little bit slower than Mars. The squiggly line there is about a year. The direct line is basically a Hohmann transfer, but you're doing it to any location on Earth's orbit, so you can launch anytime. The squiggly line is about a year, so you got 8 months plus a year, so a year and 8 months to get there. And what has been shown is it uses about 30% less energy than a direct Hohmann transfer. So you're just drifting into Mars, either it's catching up with you or you're catching up with it very slowly. And you get captured dynamically by the gravity field. You need no delta V to go into orbit. It's pretty tricky. And as you can see here, it uses nonlinear dynamics to calculate that the window of where you need to position your spacecraft as you approach Mars. It uses chaos theory and nonlinear dynamics, which is a very exciting topic. For those of you that may have seen Jurassic Park, Jeff Goldblum's character was trying to describe chaos theory to the lady here by saying just a small difference in the position of your hand can make a drop of water roll off to the left. A tiny move of your hand, it'll move off to the right. A great change based on a very small input. And similarly, when you're coming into Mars orbit under ballistic capture, you have to get it just right. And you enter what's called the weak stability boundary, and you do a couple of revolutions around the planet, and then you do a small delta V on the order of tens or maybe 100 meters per second, not very much, and you spiral down to the surface. So ballistic capture. Again, it was popularized by Edward Bell Bruno of Princeton University. I've met with him. We've discussed this several times. The technique has been used several times by NASA. Here's a few. The JAXA, Japanese Space Agency, did it in the Hiten mission, I believe, in 1991. And then a few other missions that have actually used ballistic capture in their trajectory. In discussing this with Dr. Belbruno, we had several sessions together, and when I expressed my suggestion to launch from the moon and this proposal right here, his comment was amazing. So that was good to hear and some validation. So the way we would launch from the moon, a couple of ways I mentioned, the magnetic railgun. Of course, you'd have to have a non-compressible payload because you're looking at a launch rail of less than 10 meters long. So you're going from 0 to 3 kilometers per second in less than 30 feet. So that's some serious G-force, on the order of 60,000 Gs. So even metal starts to turn liquid at those forces. So you couldn't carry any organic material. Of course, you need to carry some propellant with you because you need to do a delta V burn later on. So you need to have the mechanics of a rocket engine. So it remains to be seen if spacecraft could even survive that launch. So we have some other options. A light gas gun, just started to do some research into that. There's on the top right there, you see the NASA's or the Navy's railgun. And it reaches 7 kilometers per second. And then I forget who did this. Some university made this this light gas gun, the picture in the lower right, and it achieves about 4 kilometers per second, so pretty fast. The downside of this is, of course, that the spacecraft needs to survive the launch. That would be a good thing. So what I'm leaning towards now is just standard chemical propulsion. What you see here is a picture of the ESA lunar lander. Mine would be a lot smaller than that, about 1/10 that size. And if I'm proposing to launch 2 kilograms, according to my calculations and some help that I've received, you'd have a 40 kilogram total launch mass from the surface of the moon. So, we're talking about, 100-pound rocket. That's easily doable. Of course, we need to get it, to the moon and everything, but that's easy, right? Okay. So chemical propulsion has a lot of advantages. It's well known. Lower G, so you could send medicines and organic materials. It has, when you do a rail gun, you're booking it the time you're at the end of that rail, and you don't have a lot of control after it reaches the end of the rail. So not a lot of trajectory control other than the mid-flight delta V burn. Of course, it requires fuel. The advantage, I should have mentioned that the advantage of the rail gun is it could be done totally solar. You charge up your capacitors with solar energy, and according to the calculations I've done, you'd be able to store up enough energy to do a launch to reach 3 kilometers per second about once an hour. And so, if you were able to do 2 kilograms an hour for a month, that's a ton. Anyway, so there is some potential there. Chemical propulsion, of course, is attractive. You do need, of course, there's more fuel, extra cost. Then you need to get the fuel to the moon. And, I'm hoping to get a technology demonstration of a railgun on the moon soon. And the advantage of it is that it could easily be launched as a secondary payload because there's no fuel or anything. Trying to get a small spacecraft to the moon with fuel on board would not fare very well as a secondary payload, I don't think. And so that would, it'd be much more expensive, of course. And so what I'm developing is a reusable booster, kind of like what Elon's doing here on Earth, but do the same thing on the moon. So you'd launch the booster, you'd get the spacecraft on its way, and then it would come back to the lunar surface and land again and be ready for the next flight after refueling. So the next steps, I could use some help. Currently, I've been doing all this myself. I'd like to be able to model this mission in some known software. Analytic Graphics SDK Astrogator would probably be the program of choice, except it's pretty expensive. And so what I've been using instead is a open source program from NASA called GMAT, General Mission Analysis Tool. It's being kept up to date. There's a team at JPL that's actually working on this, Stephen Hughes and his team, and they've been very helpful. What I'd like to do, they did implement a non-linear optimizer in the last version, the 2018 version. So I'd like to see if that would lend itself well to my mission proposal. I believe we'd have to write the nonlinear, the math for, the math done by Belbruno would need to be done. So that would be some work. So I've been developing my own launch platform. I have a test facility at Hayward Airport. And what you see there is a static test stand that's been working quite well for me. I'm developing a vertical takeoff and land boost system right now. The thing that's been taking a long time is the control software, and that's what I've been working on. Again, evenings and weekends, it's just kind of hard to focus on this. And you notice that the test stand there, you notice it's made, there's a lot of wood there. For what I'm doing, it works just fine, and it's very inexpensive and easy to modify as I do different configurations. Okay, switching gears. The Mars atmosphere laser. So as you know, the atmosphere of Mars is like 95% CO2. CO2 lasers are well known on the Earth. And so I was proposing that it would be easy to make an open cavity laser on the surface of Mars. All you really would need to do is just in the open atmosphere, just put 2 mirrors up and put a discharge in there, and you'd have a laser. So 90% of the mass of current high-power gas lasers and other lasers, like the kind that's used at Lawrence Livermore, the National Ignition Facility. If you've ever taken that tour, the building that houses that machine is about the size of this building. And it required 12,000 tons of steel. It required a huge vacuum system and a support infrastructure. So what I am developing is actually an inflatable laser that could be deployed on the surface of Mars that would need very much less infrastructure. So the uses of a laser like this, although it does require a lot of electricity, I'm not going to say it's like for free. So we need one of these, I'm guessing an early prototype would be about 1 kilowatt. It'd be nice to have one of those little nuclear reactors that we've been seeing here at the conference these last few days. I'd like one, so if anybody has one, if I could borrow it, that would be great. I'm going to show a little video in a second. I hope it works on this system, where I took a standard CO2 laser and I opened it up. And then I went to a gas company. They're pretty popular for doing welding gas and stuff. And I said that I needed a composition of gas that was 95% carbon dioxide. And then I'm going to forget the percentages because I'm kind of nervous up here. The next slide, actually right on the next slide, it'll show the actual percentages of, I had this, a tank of Mars atmosphere gas made for me. And it wasn't cheap either. It was about $1,000 for a little tiny tank. And so anyway, some of the uses for such a laser on the surface of Mars, I'm going to demonstrate how you could actually fuse Mars regolith with a 1 kilowatt laser and fuse the regolith to glass, and you can make bricks. You could use it for welding construction. And then I'm going to show, kind of looking forward a little bit, why not, inertial laser fusion, similar to the National Ignition Facility. I think the reason we haven't achieved fusion yet, because we've been building the reactors on the wrong planet. We should be doing it on Mars. And also for ground-to-space propulsion, like Project Starshot. And because the atmosphere of Mars is of the perfect composition and also of the perfect pressure at the surface of Mars to support an open cavity laser. That's what my experiments proved, is that I'm using torr as my pressure measurement. The pressure of Mars is about 1/100th the pressure of that here on Earth, or 5 to 10 torr, and that's exactly the pressure that a CO2 laser uses. So this is the tank of gas that I had manufactured, and if you can see there, I'll read off the percentages for you. So the balance is carbon dioxide. So whichever left over is pure carbon dioxide. And then so there's 2.7% nitrogen, 1.6% argon, 0.13% oxygen, and 0.08% carbon monoxide. So I had that made for me. And then what I did is I used a party balloon manifold system, thanks to Home Depot and some fittings. And I got some smaller tanks of each of these gases. And so I tried to mix different percentages just to see if, if this wasn't exactly the makeup of the Mars atmosphere. Basically, when I developed my laser, I could not get the gas to stop from lasing. Whatever I added, it still wanted to laze, bright as the sun. And I think the next slide. So this is what it looks like at my shop in Hayward. Of course, it has a glass tube because I'm in the Earth atmosphere. But on Mars, this would be a purely open cavity. And one of my technology demonstrations is to get about a 1 meter inflatable laser to Mars. It would transport in a package, no larger than your fist, and then using the Mars atmosphere itself, you'd inflate it and do the mirror alignment, and then you could wrap it with solar panel material, charge up some capacitors, and do maybe a 10-watt laser demonstration. So here's where I took a standard CO2 laser. I broke it open and filled it back up with Mars atmosphere gas. You can see the balloon manifold there. And this was the first time I lit it up, and I'm sending it through a 90-degree mirror there, and then down into Mars simulated soil. This is some soil that I purchased that is the closest analog that we have to Mars soil. It's obtained from a volcano in Hawaii, and I added some secret herbs and spices, specifically calcium perchlorate and sodium dioxide. So this stuff is like Mars soil right here. And this thing was lighting up like the sun. And you can't really see, but it creates a little tiny marble. It melts it into glass. So a standard laser, is made like you see in the picture here. You got a laser cavity in the center, and then you have two mirrors at either end, and then the light comes out of the partial reflecting mirror at the one end. So another thing I'm proposing is a spherical laser, which would make sense in the open atmosphere of Mars, because you wouldn't need to have a large infrastructure to support it. You wouldn't need to have a large vacuum system. So you could actually build this in the open atmosphere of Mars. And you can make it arbitrarily large. I mean, this thing could be big. So my proposal is to have two concentric spheres. The inner sphere is fully reflecting, and the outer sphere is partially reflecting. And then so from an external observer, you would see the laser light appear as a dot at the center. Of course, the laser light is going out in all directions, but it is coherent light. And so you have a hyperbolic reflector, as you see on the upper right, to focus that down into a pinpoint to do some work. And the work could be inertial laser fusion, as you see on the left there. You put them in a configuration as you see there. You could use it for ground-based propulsion. You point the laser up, and then you have a spacecraft with a solar sail moving away from the planet, and just the pressure of the light itself could accelerate it close to the speed of light. Similar to, was that Stephen Hawking's and team, this Project Starshot. So that was quick. You can contact me here. Right now, if you went to that website, you're just going to see some information on yet another project I'm working on. I'm developing a remotely operated jetpack, which has been kind of fun. So anyway, that's all I have. Any questions? Thank you. Yes?
Yeah, Jeff, I've been to your website. There's some cool videos.
Thank you.
On the railgun, have you work that was done in the 1970s, 1980s at MIT Space Studies Institute on mass drivers?
I have not. That's one of the reasons I came to this conference, is to get connected and find out information like this. Who else has been doing this? I've been kind of working pretty much by myself, alone in my shop for like the last 4 years. So I needed to get out more, and that's kind of why I'm here. So thank you for that. Please follow up with me later, and I'd like to get more information on that. Yes, in the back. Thank you.
The
So-
payload size, the 2 kilograms, I would be concerned we wouldn't have enough for reentry shielding when we got to Mars. Would that be a problem?
Yeah, the question was, how are you going to handle reentry? That's a darn good question. So what I'm, because it's pretty small, but yes, it would definitely burn up in the atmosphere. I have tried, or I'm thinking of a couple of solutions to that. One is an airbag deploy, and just bounce it off the surface. You'd aim for a crater, and then you'd fill this crater up with all these little 1 meter, inflatable bags that have 2 kilograms at their center. So that's one option. My first technology demonstrations, I just want to be able to make it to Mars. It'll burn up in the atmosphere. In fact, I'm probably going to put some sort of, heavy metal in it so it like burns brightly, so we can visually see it when it enters the atmosphere. One nice thing about the railgun system, or both of these actually, is I'm proposing you could do it with a feedback control mechanism. If you were off target when you got to Mars, you just radio back to your launch team, 9 months later, say, hey, you were 10 miles to the west. Can you adjust a little bit? And so the next launch, they'd adjust a little bit, see where how it made it, and then do this feedback iterative loop. So eventually you'd be nailing it every time. And through feedback, you'd be able to get very accurate to the same location every time. And so one use might be to get supplies there before we send men there, and or women, I should say, people. And so you have a stash of supplies once you get there, and they'd be all nicely collected in a crater, because it would be good because it'd bounce and it'd stay hopefully inside the crater. So thank you. Yes?
Yes, you were using as your initial example, trying to get some medicine or something to Mars, but this that you described is that it doesn't give you, well, you can launch every hour and any time. It doesn't hit Mars until Mars catches up to it.
Right, right.
Right, so that isn't really, but yes, sending raw materials
Mm-hmm.
that we don't have, like refined metals that you
Right.
yeah.
Yeah, so the time that it takes, depending on the position of Mars and Earth at the time of, let's say, the emergency. If there was a flight upcoming already scheduled, you just want to be a secondary payload on that. And if the Earth and Mars were perfectly lined up, I would agree that a home and transfer would probably get your stuff there the quickest, but it'd be very expensive if you launched from the Earth. So what I'm proposing is just to have an infrastructure on the moon. And so, of course, you'd need to get this medicine, whatever we're discussing, from the Earth to the moon, and then from the moon to Mars. So it'd be a 2-step process.
And we're talking about the time of actually getting it on the surface of Mars, or do you have to make any?
I'm sorry, what's the question? Oh, yeah, so this is no magic bullet. So it still takes about the same time as the home and transfer. But if you miss the 2-year launch opportunity, this would be at a great advantage. Yes, it takes about the same time, but the advantage is that you can launch anytime. So let's say it takes a year and 8 months to get there. And let's say that you're right, you just missed the home and transfer window. So you're talking 2 years plus 8 months for a direct flight. So you just beat that launch by about a year. So it's not always optimal to launch from the moon, but half the time, if you're within a year of a home and window, then you might want to wait. But if it's like more than a year out, then my suggestion would be more efficient.
A lot of applications.
Yeah.
The Mars Direct plan is about every, it's 25 and a half months or something, but 6 months for people and 9 months for free.
Right. Yeah.
This might be a little bit more says he needs, 50 to, he needs under $100 a pound to Geo to be able to collect power, beam it down to Earth, and sell electric power under the, coal-powered, cheaper than coal-powered, plants.
Right.
And he's trying to figure out how to do that. I've been saying you need a system that moves your equipment back and forth and then, and you reuse it. But he's saying, but I need the raw, aluminum and materials that you're using to move up the other stuff. But this could put a lot of, relatively cheap, aluminum and glass parts in, there.
Yeah, I think for like construction materials, since you're only just, in my proposal, 2 to 5 kilograms, it would take a lot of launches to move materials like that. So this would be for very high value, energy dense or whatever, product you need to get there. It would need to be quite valuable, I think, to make this worthwhile. So the real efficient use is like the BFR and getting tons on Mars all at once. I mean, that's the way to go. If you have that opportunity, that's the most efficient way to get stuff to Mars. And another, you'd mentioned, beaming power down to, my proposal uses all existing technology. I mean, yes, we need to get a launch infrastructure on the moon, but it's nothing that hasn't already been done before.
Well, this is all stuff that we've done before in various ways.
Okay, thank you.
I mean, we do beam power down to Earth, but it's only in,
Yeah, very small, very, very low power. Yeah, yep, exactly.
beaming power.
Yeah, there you go. Yes. Possibly. So, I'm kind of suggesting that, kind of off topic and not to your question or comment, that we might not want to terraform Mars because the atmosphere is so perfect for one of these lasers. We could make arbitrarily large lasers that, imagine you put 2 mirrors in geosynchronous geosynchronous orbit around Mars, and they're tangential that go through the atmosphere. This is way out there because you'd need phenomenal electric power, and so right then you'd have like the Death Star, and so you could beam power. You could beam power directly from the atmosphere of Mars all the way back to Earth that way. I mean, that's silly talk, but I mean, it's just fun to think about.
Beam it to a satellite. Phobos is a great place to be producing satellites and stuff.
Yep, that's why we're here to explore new ideas, isn't it? Yep, exactly. In front here?
So Jeff, the goodness of your Mars laser is not that you can make it big, but that it is small.
Exactly. Could be either. Yeah.
So what I'm thinking is, if it is really that small and that portable, and your parabolic mirror can slew around, you've got a 3D printer.
Right. Yeah, that was one of the suggestions that I had is you could actually use the Mars regolith as material inside the printer, and you can fuse the Mars regolith and make bricks or other building materials directly, just heating it and melting it and shaping it.
With the habitat directly.
Yeah, exactly.
Or put up walls.
Yep.
What the railgun proposal, it seems to me that you don't need an acceleration of 7 meters a second like they had on that Navy railgun.
Right. You do not.
You could both slightly, lengthen the barrel and slow the acceleration by half, and you can then reduce the acceleration.
Yeah, so what I need is one about half the size of the Navy railgun. And a little background, one of the reasons, excuse me, one of the issues around the railgun, recently we were doing some experimentation. So you need to dump like 1 million amps into this thing, and which isn't so hard, but you don't want to do it as fast as you can. You need to time it and slow down that discharge to travel and follow the projectile as it goes down. You know, it's like milliseconds, not nanoseconds. And well, actually at that speed, it's pretty fast. But at any rate, you need to control the spark of millions of amps, and so that's difficult. When we were developing this, the friend that was helping me design the railgun, he did some prototypes, and he built one, a railgun about a meter long, and he was powering it with some incredibly large capacitors, and he was using 1-inch diameter welding cable. And what happened was, this cable is made of multiple strands, right? And so when they dumped that 1,000,000 amps through this welding cable, it exploded. And it didn't explode through heat or anything. It was only because of the magnetic repulsion produced in each individual copper strand. This thing exploded, and a little unsettling. As you can imagine, it was a good thing that there was nobody near that when that happened, but it was like, and destroyed. And so there are some special switching mechanisms that you can use. So in my work at my hangar, I've done some chemical propulsion work, and it's a little story. I guess we have some time because there's nobody, you know, so I'll just tell some stories. I purchased some concentrated hydrogen peroxide because I wanted to learn propulsion about 5 years ago. And so I thought, what better way to do that than to buy some rocket fuel? And so I bought about 5 gallons from this company in Montana. Some of you might know them. And so I had that on hand at my hangar for several years. And recently, though, decided to just give it away because every time I went to my hangar, I would open the door at an arm's length, thinking that there was some kind of backdraft activity going on because it had evaporated or something. It just made me nervous. I didn't want to work in my hangar with 5 gallons of extremely dangerous material right next to me. When we test the specific gravity and the concentration of this hydrogen peroxide, it's about 90% hydrogen peroxide. We had some friends, we were in hazmat suits and we were testing it, and we had about a tablespoon left over, and we didn't want to dump it back into the container. So we're, you know, what are you going to do with it? You know, so we decided to go out into the gravel by my my hangar next to Hayward Airport, maybe, I don't know, 100 feet next to the runway, and it was only like a tablespoon. You know, that's not going to do anything. And so, you know, in a hazmat suit, so we went out there and I dumped it, and he actually dumped it. I go, you do it, I'm not going to do it. And so he took it out there, dumped it down, and we could hear it sizzling and just bubbled a little bit. I'm like, oh, no problem. So we walk away and we hear this sound that's like starting to rumble. And what happened was, so hydrogen peroxide breaks down into superheated steam and oxygen, and it makes good rocket fuel. But it's also very energetic, that I found out. What happened was that tablespoon, it expanded and superheated this cloud of super dense white steam that was, I mean, it was broad daylight and you could not see an inch into this thing. It was just a 50-foot cloud of steam that rose up like a mushroom cloud. And then I had this 50-foot cloud drift across the runway of this this active professional airport, you know, and I would say realistically within 2 minutes, it seemed quicker than that, security was there right away. And they said, what the hell was that? And I just said, it was just hot water and steam, which is exactly true. And they're like, that was just steam? I'm like, yeah. Because it looked like it, because it dissipated and looked like fog and stuff, and it just went away. So it didn't look like smoke. And so I could honestly say, you know, it was just steam. And they looked at me, and I'm like, what? I'm not lying. And he goes, okay, we'll let you off this time. But anyway, so I got rid of that. And so I thought I'd go, well, okay, well, that's too dangerous. I can't learn rocket propulsion by playing with rocket fuel. So what about railguns? And then so we did the railgun thing, and then we had this welding cable explosions. So this stuff is dangerous. Rockets are hard, so I'm not naive enough to think that this is easy stuff. So, but it's quite a challenge, and it's been quite a ride. Yeah. Yeah, exactly. So.
You get any arcing and stuff and wear on the railgun?
Yeah, that's a big problem. Just yeah.
Before you have to repolish it and recoat?
The question is, how often do you have to recoat and repolish your railgun? About 3 times per shot. What I mean is, what I mean by that is, what happens is that oftentimes the projectile simply gets fused right in the rail, and you have no activity. It's just a big explosion, and you have a melted mess. So yeah, it's not rocket fuel, but it's just as much. You're getting something small to 3 kilometers per second, whether you use rocket fuel or railgun. You're talking,
3 times per shot? Or
I was joking. What I meant was, yeah, what I meant was is that you need to polish it 3 times before it finally works.
Oh, okay.
Yeah. I mean, what it does, it locks up. You got to rebuild the rail. Try it again. It locks up. Basically, what you want to do is you want to pre-inject the projectile so it's already moving before it gets into the magnetic field. And so that's one technique. But yeah, it's.
What are you using to delay the charge?
Well, I would have to defer to my partner who actually designed that system. But if you want to contact me after, I can follow up on what that's, the electronics.
Is this Hayward, California?
Yes.
Oh, okay.
Yeah.
I live in
Yeah. No, they don't know I'm here was the comment, which is quite interesting because I just, as you saw, my static test stand is indoors. My door, my hangar opens up, the whole side of the hangar opens up. And so I'm doing my test launches indoors, basically, with the door open. And it gets kind of smelly in there. But the airport security, they come by all the time to watch, and I have, neighbors next door that own private jets, and, I get free rides from them. It's been a lot of fun. But so far, they love me there. I just pay my rent in time, and I haven't blown anything up yet. So
Hayward's a small airport.
it is. Yeah, it is a small airport.
I tried to Google it.
Yeah.
Hayward.
Yeah, the call letters is HWD if you want to Google the Hayward Airport. Say again? Yes, there is. I can't really say that, but the person right next to me has got something that's pretty amazing that they're going to demonstrate in just a week or 2. Yeah, the comment was, aren't there flying cars there? And yes, there are. Yeah. It's the reason I was kind of interested in that is because I'm building a jet-powered drone. Basically, I took a quadcopter, took the propellers off, and put jet turbines in their place. And I've been working on that for a few years, and the goal is human lifting. And if you go to my website, you see this thing that picks me up, a little bit. I put on a harness. It's hovering above me, and there's a cable that comes down, and it picks me up and then sets me back down. So I've been working on that, and that's been a lot of fun too. Yeah.
The range and flight time.
The flight time for this is very, very short. 5 minutes. The use case would be a rescue situation like a structure fire where a fire truck rolls in with one of these in the back of the truck, and there's somebody stuck up on the roof, and you need to get them down really quick. So you launch it. You're in proximity to the situation. You couldn't use this thing, number one, for transportation. 5-minute flight time, not going to work. And you can't use it to go look for people. You got to be right there. And so if there's somebody stuck on a burning roof, you can fly up, grab them, and then bring them back down to safety. Another use might be high voltage line maintenance. Right now they use helicopters to just even carry a box of tools up to the workmen that are up on top of the high voltage towers. And unfortunately, helicopter pilots get killed every year in working on power lines. So this would be another use.
What's your fuel?
Kerosene. Yep. And I found that hydrogen peroxide and kerosene is also quite energetic. You had to find out, right? It's like, I wonder what this would do.
If you want to get an extreme boost, throw in a little bit of kerosene, and yeah, you get some extra power
Yep.
out of it. But it's very low energy.
It is compared to, liquid oxygen and methane, or liquid oxygen, liquid hydrogen. I mean, those are, but they're cryogenic. The advantage is hydrogen peroxide and kerosene can all be used at room temperature, so they're easy to work with.
The first jetpack was hydrogen peroxide.
Right.
So that was just almost seconds, not many minutes.
Yep. Any other questions? Yes, here.
Yeah, if I want to find out more about using lasers to propel
Yes.
would I Google Project Starshot?
Absolutely.
Or give a better-
That would be the way to do it. Just Google Project Starshot, and they talk about an Earth-based laser that they were proposing to propel micro spacecraft. Just that big. The solar sail. They launch it up there, get it into orbit, and then blast it with this laser. But you're going through the atmosphere, so I'm not quite sure how.
Would that laser have to be on Mars?
A lot smaller. I mean, the size that I really haven't done the calculations, but it would definitely, because you're not going through the Earth atmosphere and you have a lot less gravity. Again, the reason we haven't done some of these things is I think we've been doing it on the wrong planet. We need to be doing these like fusion energy and light sail propulsion on Mars. It should be. That would be the hope. Yeah. Okay. Thank you, everybody. That was fun.